G'day everybody, my name is Reese and this is my video series, How to Do Cool Things in SPSS in Less Than 10 Minutes. In today's video we're going to be covering a very complex topic, confidence intervals in SPSS. Due to the nature of the topic, we're going to be breaking the rules just a little bit and exploring confidence intervals in SPSS in less than 15 minutes. Due to this complexity, I think it's really important that we start today's session with a detailed plan, a detailed overview, and that's exactly where we're going to jump straight into it. To understand what a confidence interval is, we first must give this video a little more context. Let's start by exploring why we collect statistics in the first place. In research, we are always looking at defining or exploring different theories and ideas, and to do this we need data. More specifically, we need information from our populations of interest. Statistics are vital because due to practical, time and financial constraints, we can never record information about our whole population of interest. Instead, we can usually only take a snapshot of the population, called a sample. The whole purpose of statistics is to take a sample from a population and use statistical theory to infer things about this population. For example, we can take a sample, measure a variable, calculate the mean, and use this sample mean to best represent the population mean. Using this sample mean, we can have a pretty good guess about what the true population mean would be. We can go one step further by calculating a statistic called the standard deviation, and can now measure how much variability there is around this sample mean. There is one small problem here though. Our sample isn't the population. It isn't perfect or 100% accurate. For example, it would be extremely unlikely to take a random sample of people, measure their IQ, and get the exact same population IQ and standard deviation that one would achieve if they had sampled everybody. To extend this idea further, imagine that I took a random sample, calculated the mean IQ of my sample, and then took another sample and did the same thing. I'm probably going to get similar mean IQ scores across my samples, but very unlikely to get the exact same value each time. This is what we call sampling variability. Each time we collect a random sample, we get slightly different results. Let's observe the effect of sampling variability firsthand. To demonstrate this effect, I'm going to control what my population actually looks like and use data simulation. Let's pretend for a moment that I have information about every single person in Australia and I know their IQ exactly. Let's pretend the mean IQ for the Australian population is 100 with a standard deviation of 15. I'm now going to take random samples of 50 people and try to estimate this true population mean of 100. Let's see how close I can get. Okay, let's have a look at this little applet here which explores sampling variability. Okay, so if you wanted to, you could have a go of this yourself by typing in the name of this applet into Google, but what I'm going to do here is I'm going to fix some of the parameters of my population here. So remember we said we're going to have a mean of 100, a standard deviation of 15. I'm going to randomly sample one sample of size 50. Now when I click this sample here, watch what happens. That's the known population mean straight down the middle, and this little dot here is the random sample which I just drew, and here's the statistics from that particular sample. I can go ahead and do another sample. You see I get a slightly different number, I do it again, and you can see every single time I take a sample I get a slightly different mean, but I'm still very close to this population mean. I can continue to do this over and over again, trying to estimate the population mean here using a random sample of size 50. As you saw there with the simulation demonstration in that app, each random sample that I selected had a slightly different mean. Again, this is what we call sampling variability. We can actually estimate this variability in those particular samples using a statistic called the standard error. We won't go through the mathematics in particular in this video. but if you were interested, you could explore the calculation of the standard error. Using this particular statistic, we can calculate what is called a range or an interval, or more specifically, a confidence interval, in which we can estimate the true population mean. In that little app, you would have seen little green lines appear around those random means which I was generating. This particular interval is called a confidence interval. Let's take a look at the app again, and we'll explore this term confidence interval in a little bit more depth. Okay, so we're back in our random sampling app again. So let's go ahead and take the exact same random samples that we were taking before. So I'm going to calculate a mean. It's going to have a population mean of 15, standard deviation of 15, size 50, and we'll calculate one random sample. So I'll go ahead and click sample. You can see here the population mean of 100. Here's my sample. I've estimated the population mean to be 101 with a standard deviation of 14.92. What this green line here, this is what we call our confidence interval. So again, the confidence interval is a range in which we can be 95% confident will contain the true population mean. So again, I take my random sample, I estimate the population mean, so here's my sample mean, and then around that mean, I generate what is called the confidence interval. Now, I've calculated here a 95% confidence interval because that's what's become a standard academic practice. In theory, you can change the percentage in which you are confident, so you can make it 99 or 90, and that has consequences which we won't be discussing in this video, but you can theoretically change it. So again, this interval is our 95% confidence interval. We can be 95% confident that this interval will contain the true population mean. Or to put it in another phrase, or in other words, if we selected 100 of these random samples, so rather than just selecting one, if we were to do this 100 times, theoretically we would expect 95% of our random samples that we selected for their intervals to contain the true population mean. What we have here is an actual diagram representing just that. So what I've done here is I have randomly sampled 100 samples of size 50, and I've put them on the one plot for you. So again, the black dots represent the sample means, the green intervals represent samples where the confidence intervals actually cross or contain the population mean, and all the red intervals, they're the super dodgy ones. They're the unfortunate scenarios where if we had have selected those random samples, we would not have captured the population parameter in our confidence interval. So because theoretically 5% of these random samples won't contain the population parameter in the confidence interval, this is why the confidence interval is called the 95% range, or the 95% confidence interval. The name in itself represents or accounts for this probability or ambiguity. Alright, so I think we've spent far too long talking about the concepts behind confidence intervals. Let's jump into SPSS, shall we, and I will show you how easy it is for SPSS to give you the confidence interval for a sample. Okay, so I've gone and opened up SPSS here, and just have a little data set with two simple variables. I've just got some participants' gender and their height. It's fake data, I've actually made it up, but it suits the purpose of today's video. So I'm going to show you how to calculate the confidence interval for a mean. And in fact, it's so easy, you don't even get a choice about whether you want it or not. So it'll actually be given to you by default in many different functions. So I'm going to go ahead and click on Analyze up here, then go to Descriptives, and then go to the Explore function. So here is the Explore function. I'm going to go ahead and drag the height to be my dependent variable, and I'm going to hit OK. And here in my output window, you can see I've got some descriptive statistics. I've got the mean, I've got things like the median, the standard deviation, and we've also got the 95% confidence interval. So I didn't actually have to select anything tricky or anything like that. It was just given to me by default. And under Analyze, there's many different options where that'll actually happen, where you won't really get a choice. The confidence interval will just be given to you. There will be circumstances where you have to actually select it yourself. So I do know that if you're in compare means and you're performing a one-way ANOVA, for example, you do actually have to select descriptive statistics, which will generate the confidence intervals around the means for you. And there are some cases, for example, when you're doing regression, where you might want to grab the confidence interval for your coefficients, where you would actually have to go into the options. Is it under options? Sorry, no, it might be under statistics, where you would have to select the confidence intervals for you. But all confidence intervals in SPSS are very easy to obtain. They'll either be given to you by default, or they'll be selectable under a particular option when you're in that function itself. It's also a good time to mention that our discussions so far into confidence intervals have all been framed around the confidence interval around a mean. Now, I've deliberately done that just to keep our discussions quite simple today. However, you can get confidence intervals around a range of statistics. So, just to give you an appreciation or an understanding of that, I'm going to go ahead and perform an independent samples t-test. So an independent samples t-test tests whether the means of two independent groups are significantly different or not. And you'll see that SPSS actually gives us a 95% confidence interval for the mean difference. So I'm going to go ahead here and go to Analyze, Compare Means, Independent Samples t-test. I'm going to see whether the heights in my sample differ between males and females. Nothing too sophisticated going on here. The most important thing I want you to note is that SPSS performs the t-test for us, but actually gives us a 95% confidence interval for this mean difference here. Okay guys, before we wrap up today's video on confidence intervals, I do want to briefly touch on another concept called bootstrapping. So there are circumstances where confidence interval generation or confidence interval calculations from our samples are not ideal or not possible or not accurate enough. So these scenarios occur when our sample sizes are very small, or we have data abnormalities like violations and assumptions, or when our confidence intervals just aren't fitting very well. There is a modern, more sophisticated way of calculating a confidence interval in these scenarios though, so it's not all doom and gloom. This modern concept is called bootstrapping. So bootstrapping is when you take a random sample just like we were doing before. So to make our example again, taking a random sample of size 50 and calculating people's IQ or measuring people's IQ. But rather than mathematically calculating the confidence interval the way we were before, this bootstrapping technique is a resampling technique. So what we actually do is, and this diagram next demonstrates it perfectly, we calculate our random sample just like before. So at stage 1 we have our sample. And then at stage 2, we take many samples from our initial single random sample. So at stage 2 there, we call them our bootstrap samples. So there's thousands of them. So computers do this process for us. It's very quick, very easy in modern times. These samples have to be done with replacement. So it's possible for an individual to be sampled more than once in any one bootstrap sample there. So we take thousands of those bootstrap samples, and then at stage 3 there, we make a distribution, or SPSS makes a distribution for us of all those thousands of bootstrap means put all together, and it generates a sampling distribution of the bootstrapped means for us. From this distribution, we can actually recalculate a 95% confidence interval, and we call that the bootstrapped 95% confidence interval. Let's go ahead now and demonstrate bootstrapping in SPSS. So it's a nice and easy process. Whenever you go to perform the analysis that you're interested in, doesn't matter which one you're doing, I'll choose one at random here. You select the variable that you're interested in just like you normally would. However, rather than clicking OK straight away, you select this button here called bootstrapping. And there's lots of options here to select. We'll perform bootstrapping in a very simple context today. You select this little button here, then hit continue. Now before I click OK, I will just warn you, due to the resampling process of bootstrapping, it can take a couple of seconds for the analysis to be generated. If you're using a rather slow computer, this can be a little bit longer, so just bear that in mind. So you hit OK, and you can see here I've performed a descriptive analysis. I've been given random stats like the mean and the standard deviation, but I've also been given a bootstrap confidence interval. Now bootstrapping again can be performed in any analysis in SPSS. Nice and simple. Okay, that wraps up this video on confidence intervals. Hopefully by now you have a basic understanding conceptually of what a confidence interval is, and you're also confident in your own ability to explore SPSS and get your own confidence intervals both in the conventional manner and via bootstrapping. We've merely glazed the surface of the theory behind a confidence interval and didn't really go into the mathematics behind it either. But hopefully just having a taste of what confidence intervals can give you, you're now ready to embark on your own individual assessments or any future studies, and you can appreciate the importance of confidence intervals. Thank you very much, guys. I'll catch you next time.